going to start the session of this afternoon. First of all, I'd like to introduce the members of the jury. The first one is Liu Xiangmin 教授 from S502.
Good afternoon.
薛亚明教授 from 东研院。郑优哲 from 淡江大学。刘腾秀 from 阳明交通的执行。I'm Coaching Wu, going to be the chair of this session. And then I'd like to ask the captain of each team to introduce your team and team member. Start with the reporter.
Good afternoon, everyone. We are Team ND Fresh from Minot High School in Taiwan City. My name is Lin Guoli, and this is Lin Yunhong. This is Wu Junde, this is Lin Yiting, and this is Lin Hongyu. Thank you.
All right, thank you. Reviewer?
Good afternoon, everyone. We are Zhang Hao. We are from Chai City. And this is Su Yu, this is Tommy, this is Naomi, this is Su Yu, and I'm Chen Junhao.
All right, thank you. Reporter?
This is Born Hamid Yilun from Team Beijing, Shanghai Girls Senior High School. My teammates Xie Beijing, Zheng Youyun, Han Weimin, Huang Xiuan. Thank you.
All right, thank you. So, since the problem has been chosen, this one is going to be the number 3, green on the rock. So we're going to go into the session of preparation of the reporter. 5 minutes.
Number 3.
Oh, God, please write down the representative of your team member. So it was supposed to be a question. All right, Laura, you got 12 minutes for presentation.
Hello everyone, my name is Robert Lin from Bangladesh. The topic we're going to present is string on the rod. And first of all, that's our problem statement. A washer on the vertical steel rod starts spinning instead of simply sliding down. Study the motion of a washer and investigate what determines the terminal velocity. And our main focus is what determines the terminal velocity. And here's our outline. We're going to divide it into phenomenon, the experiment setup, theory and data analysis, and the conclusion. And here's a phenomenon. So we make the rod spin down to the bottom of the to the bottom of the rod. And this is a top view, and this is a side view. Here is our experiment setup. We have 4 different rings and a rod. And here's our experiment parameters. The two parameters that we will change is the inner radius of ring and outer radius of ring. And we will derive from the equation that will be later mentioned that the inner radius might be the major factor that affects the terminal velocity. And what didn't change in our experiment is the rod radius and the friction coefficient due to the limitations and the accessible resources. And here comes our theory. And this is our model 1. This model is based on the washer and the rod. And omega s is the angular velocity of spinning. The omega p is the angular velocity of precession. And r1 is the inner radius of the ring. The rc is the distance between the center of mass of the washer and the z-axis. And the z-axis is the rod. And also omega s and omega p is the most important parameters and among them, since we're going to discuss it later. And this is our model 2. We draw this model by the Ura angle system. So we define the omega p as the phi dot. So every calculation, we can find out that omega 1, and omega 2, and omega 3 as the value that was shown on our PowerPoint. And in this case, we set the center of mass of the washer as the origin of our coordinate, and we see the the precession of the washer as the rotating of 1, 2, and 3 axis. And here comes our angular acceleration. And the angular acceleration equals to the omega over dt, and the omega equals to the total angular velocity, which equals to omega s sine theta omega p d. And since z equals to this things. Thus, we can find out that alpha equals to omega s omega p sine theta cosine theta e3 plus omega s omega p sine square theta e1. And here's our moment of inertia, and we're not going to spend time on this page since we can get a lot of information from that. And here's a torque analysis. We get the torque from the Ura angle. And after the calculation, we can find that tau 1 and tau 2 equals to 0. And the tau 3 equals to R3 omega s omega p sine theta and cosine theta. So we're going to focus on tau 3 on our next page of our PowerPoint. Here comes the tau 3. Tau 3 equals to R1 cross Fk, and Fk is the kinetic friction. And when the ring reaches the terminal velocity, it will equal to the gravity, which is mg. So we can find out that kinetic friction equals to mg cross sine theta. And after equating, we can find out the relationship between the omega s and omega p, which is shown in this, which is the omega s omega p equals to r1 mg over r3 sine theta squared cosine theta. And next page. And we can get this two equation from this two model, which this one means the ring, and the velocity of the yellow point is r1 omega s, and this model, the blue circle is a rod, and the velocity of the orange point is omega c omega p, and because their terminal velocity remains the same, so we can find out that this one will equal to this one, and so we can get the relationship from it. And here's the top view of the experiment. The upper equation is the equation of the ring and of the ellipse of a ring, and this equation is the equation of the circle of the rod. And since they have two contact points, so and their x-axis is the same, so we can find out that RC equals to root r1 squared sine theta squared minus r2 tangent theta r2 squared tangent theta squared. And if we take the two equations into a simultaneous equation, we can find out that omega p equals to these things. And this is our theoretical value for omega p. And since we have both RC and omega p that we calculate in the PPT that I just mentioned before, so if we bring them to this to a theoretical terminal velocity, and the terminal velocity will equal to this thing. And here comes to the data analysis. Since in our equation there aren't any parameters that related to the inclination angle, so instead of calculating by the equation, we just measure it. And here's the four different parameters of our ring, and the downward is the inclination angle that we measure. And here comes the result. So you can find out that there is still a big gap between the theoretical data and the experimental data. And because we see that the theoretical data doesn't consider the sliding motion, so the gap between them is the sliding motion. So this data needs to be corrected. And this is the displacement to the times chart, and we can find out that and the diagram means the velocity, and we can find out that the diagrams is becoming bigger and finally reaches the terminal velocity. And here comes the terminal velocity, and is the relationship between R1 and the terminal velocity. And R1 is the inner radius of the ring. And we can still find out there's a large gap between the theoretical point and the experimental point. So we still think that it's the sliding motion that we haven't calculated and in the theoretical equation. So, and here's our correction. Since the kinetic energy and rotating energy remains the same, so we can find out the potential energy, and the potential energy will equal to the work that the kinetic friction works. So after calculating, we can find out the velocity of the x-axis and y-axis, which is right there. And so we can find out this is our modified, and this is the omega p and the Bt after our modification. So this is the result after our modification, and the blue dot is the modified data, and the orange one is the experimental data. And the theoretical values lie within the error bars of the modified experimental values, and the correction is correctly made and sufficient. And we can find out that after the modification, the two data highly fits. And here comes the terminal velocity after being modified. So we can find out that after we consider the sliding motion that affects, the blue dot is the modified data, and the orange one is experimental data. And when the inner radius increases, the terminal velocity will also increases. And here's our conclusion. The terminal velocity will equal to this, which we just calculated and mentioned before. And the modified terminal velocity will be like this one, and plus the sliding motion that we didn't calculate at first. And what determines the terminal velocity? The major thing that determines the terminal velocity is the inner radius, which is defined as R1. And the kinetic friction also, we should consider kinetic friction instead of static friction, because we will have to consider the sliding motion. And this is the end of our report. Thank you.
Yeah, thank you. Question from opponent for 2 minutes.
I want to ask, how does it spin only rotate around the center base? How does the water spin?
I'm not sure what you mean. It was spin like this. It was spin. I'm not pretty sure about your question.
You give it
Or can you draw? Or?
you give it a, okay. Maybe we can discuss it in next
In the
time.
discussion,
Okay. And you sure you release the water in a level, not with a little angle or some.
Actually, to be honest, there might be angle, but according to our formula, there aren't any parameters that would related to the angle. So, and also before the velocity reaches the terminal velocity, the condition is unstable. So I don't think it would affect.
You say you said the contact point is 2, and
Yeah.
can you explain it? And I can see your PowerPoint.
Q will be like, so this is the rod, and this will be the ring. So there will be one right here and another one right here.
And I want to ask if when you during the full time there is an angle of the inclination, right?
Yeah.
Do you observe it in every moment? Will it change its angle of inclination?
I think it won't change it since that.
Time's up.
Okay.
The duration of the opponent for 3 minutes. All right, the format, you may take the floor for up to 4 minutes before moving to discussion.
Hello everyone, I'm Eric Shea of Team Legion from Zhonghua Girls Senior High School. And today we will report you about the problem number 3 in Bring on Rock. This is our problem statement. We then focus on the motion of water and what determines the terminal velocity. An overview of the report of our observation is slide down and arrive at terminal velocity in the end. And its experiment is inner and outer radius of the water. And I think their parameter is 2 dash, so I think it can prove that. And analysis about the angular acceleration and the torque and inertia and the terminal velocity and sliding. And their conclusion is the motion of water is a inner radius is a major parameter to update the terminal velocity. And that should use the kinetic friction rather than the static friction. Sliding should be taken into account. And their advantage is a theoretical model, theoretical and experimental comparison, and the advanced result and investigation stick to the problem statements. And experimental error will isolated. And the deviation between experiments and theory will explain. And our suggestion is the lack of explain the phenomena and the lack of the parameter. I think is important, is critical. And no theoretical and experimental comparison, and lack of quantitative analysis, and lack of parameter conduct. And next we'll discuss the observation, and the map has laid down and up, and they will arrive at terminal velocity in the end, and what will lay the cause of the terminal velocity, and the friction, torque, and the air resistance affect the terminal velocity. And I think when they move, they may have the revolution and the speed and the precision. And the parameter, I give some suggestion like directed or not directed of the rod and weight of rod and weight of water and initial angular velocity. I think you can just line down and know the initial angular velocity on the directed rod. You can do that. And the analysis, this is a contrapedal force, its formula, and I think you can use it to prove how the cause of the terminal velocity. And this is the friction, the formula of friction, and this formula can prove you arrive at the terminal velocity and the collision. And I think the collision will affect the energy to make it arrive at the terminal velocity and the air resistance. And in theory about I will talk about the torque, the formula of torque. In conclusion, we will talk about the motion of water, and torque can make water spin and slide down, and the rotation and the revolution of the water, and the relationship between the radius and speed of sink. Oh, I want to start my discussion time.
All right, go ahead.
When you change the inner radius, do you use the same maze?
Actually, if you change the inner radius,
and the outer radius.
Yeah. If you change it, we remain the density the same, so it will also change the mass. the height of the washer we didn't change it, and okay.
But I don't think so. And we can go through from the KB square into mg, and it is the air resistant because the terminal velocity. Can you put the
Okay. But actually, according to the air resistance, that because I think the friction is far bigger than the air resistance, so the ratio between them I think is under 3%. So I think we don't have to calculate it in my experiment.
But friction needs to balance by the gravitation. Gravitation needs to balance by the friction. So I think the mass is a very important factor in this formula.
But actually, the mass wouldn't change the precession. So I don't know what do you mean.
Can you show your slide
Right.
now?
Okay, so. So in this PowerPoint, we talk about the precession, and actually the mass didn't affect the precession, and
So precession, how to resist it? Can you draw the torus diagram?
it's the definition. Or are you asking what is the precession or?
Can you draw the force that resists the gravitation to make it arrive at the terminal velocity? Can you draw it?
Can you repeat your question again, since I'm not so.
Draw the force can't resist the gravitation that make the washer arrive at terminal velocity.
So then there's a kinetic friction that I've just mentioned in this one. This one.
Okay. So the kinetic friction will resist the gravitation, right? Yes, it's the gravitation. And the gravitation, when it's equal, when the kinetic friction equal to gravitation, they will arrive the terminal velocity. So you can't use not the same mass to do the experiments, I think. It's my suggestion.
But actually, we can change mass since like here have the barrier of mass, so it did not affect at all. And also, the kinetic friction and the gravity both consider the mass. So in this one, and in this formula, we can find
This
that.
formula also use the gravitation, so I think it's important. Okay, next. And then can you show the direction of the torque?
No.
Okay,
like-
okay, right.
The kinetic friction and the gravity, and this is the kinetic friction, and this one is the gravity. So so
Okay,
they
I
don't have
know
to necessarily-
that. Can you show the torque, the direction of the torque?
Okay. You mean this one?
Page
Okay.
And where is the direction of the torque? Where?
The tail one is it's the torque. Like if it's changed like this, and this is the axis over there.
What's
Like
this?
like
This can.
okay. In tau one is like this one, and it's spinning in this way. So it would
And how about tau two?
tau two is like this one. So it would in this way, like and tau three is this one, and it will the torque is this way.
Tau two is this one. But it's down. It's down. So the tau three and tau one can receive the tau two.
Actually, the tau two and tau three is not upside down. It's like
So the whole motion you can you can explain it. You can show the whole motion of the water.
And this is the torque, and this is the definition. So this is
So
this one is the
that was
definition of the torque.
So because of the three torque, so they will arrive the terminal velocity.
I'm not pretty sure what you mean.
Because of the three torque, they will arrive the terminal velocity.
Actually, we
Can you show your data? Can you
so,
show your data
which-
about this?
I have to answer you this much or.
Yes, about
Okay,
this
so
question.
after our calculation, tau 1 and tau 2 is 0. So we consider the tau 3.
Do you have
And
data about this?
data about this, but this is the calculation. The data is
So you
only.
don't have the real data?
No, I mean, this thing don't have it, don't have data, it's just a model.
Okay, and can you continue this diagram? The two contact points and how
What do you want it?
the fourth diagram and release there is a gravitation. Resist the gravitation. How this?
So it is
Resist the
it's
gravitation.
still because of torque.
But they have two contact points.
So you mean
I
that,
think when I have two contact points, maybe the block needs to be thick. Sorry?
so do you mean that it should have
okay,
only
you-
one contact point? Instead of
this diagram only have the one
No,
kinetic version, so I
one
think
contact.
this will. You said you have two contact.
No,
so
we didn't see in these two points. We see the whole system as the center of mass of the washer. So actually, they only have one.
So it will make a torque, right? Can you show how to calculate it to this one?
Can you repeat your question again?
Yeah.
So what I just say is that we consider the whole system by, because there are two kind of points. So it's hard to calculate. So we see the washers, the system of washers at the center of mass of the washer. So there's only one point. But actually, if you ask the contact point, there are 2 points.
How to let two force into this force and what is this point? What is this point?
This one is the center of mass of the washer, what I just mentioned. And this one is the normal effect.
And what is the definition of the difference?
Like, since the density is a thing, so like this circle and the center is the center of mass. And so it's the center of mass of the washer.
Okay. Can you investigate the top view of the water?
So this one is where we investigate the top view of the so.
And I think I have my opinion is that for that spin rotate around the center of mass and this is right. And
You mean only one contact point?
Hmm?
You mean only one contact point?
Yes, but
Okay,
to-
so tell me
to
something.
easy to make the for diagram easier, so I need to draw it into in the one contact
But
point.
actually, if
Excuse
we
me,
reach the terminal
Counselor.
velocity,
Excuse me, time's up. We're
Oh,
going
okay.
to summarize the discussion in 1 minute.
We discussed the top. We discussed the top view, and I think the top view makes rotate around the center base, but they don't think And the side view, we discussed they have the angle of the inclination, but they didn't discuss the every angle of the inclination during the whole motion. And we discussed about the terminal velocity. They think the torque will cut the terminal velocity, and I think the whole diagram just like it, but they think the whole force diagram like this. And this is our summary. Thank you.
So you done? Okay. Now comes the question from reviewer to reporter and opponent for 3 minutes.
I would like to ask using there should be 2 contact points and
Oh. No. We all think it's 2 connected.
Short answer, please.
Okay. But in this diagram, I need to use the 1 connector. I think 2. But in this diagram,
so you say they use one to calculate.
Yeah. In this diagram, we use 1, but the whole is 2.
Oh, okay, I understand your opinion. And your opinion is the same, right? Do you have the same opinion?
Yeah, because like I just said, the density is the same, so we can only consider the center of mass of the washer. So, yeah.
So how about the torque of 2 friction?
2 friction?
Yeah.
Where's the 2 friction?
Friction of 2 contact points.
So, the center of mass is the summary of it. So we can only we can consider the center of mass of the washer.
You mean you can calculate at the same time?
Like it's a summary of them.
Yeah, you mean you can calculate the summary to stand for the whole
Yeah.
torque.
So we calculate that is equal to gravity, which is mg.
Okay, thank you.
You done?
Yeah.
Okay, all right. Here comes your preparation time for 2 minutes.
Great.
You gonna start?
Yeah.
Okay, you're gonna start. For 4 minutes?
Okay. I'm a reviewer from Zhejiang, and I'm going to present my review. First, this is the problem statement, and I'm going to summarize the reporter's opinion. First, they change inner and outer radius of the washer, and they analyze the angular velocity and torque. And they think it should look like an oval in vertical view because of the inclination. But their data from experiments does not match from the theory. So I think there should be something more to be considered. And here's about pros and cons. First, they're doing the experiments based on their theories, and they're giving formulas based on their theories too. But they didn't mention how to measure the inclination or something else. And their data is not enough. And they didn't consider enough situations. And here's some comments for the opponent. First, about pros. They have clear suggestions and points, and they point with their opinions clear. But they keep expressing their opinion instead of making sense with the reporter. So I think they didn't catch on the point. Here's about question. Opponents think the mass should be controlled since it is mentioned in the formula. But a reporter says because of the same density, the mass would be different, and it couldn't be controlled. And question 2. Opponents think friction may affect the balance of the terminal velocity, so friction of 2 connect points should be calculated in. The reporter say that they could be the 2 contact points friction could be calculated together. And here's about mixed points. They didn't consider that the inclination may be changed while the water falls until they reach the terminal velocity.
You done?
Yes.
All right, good. Here comes the concluding remark from reporter
Okay.
for 2 minutes.
Okay, about the reporter, in our discussion, the opponent mainly focused on the definition of a torque, which I think is unnecessary. And in the report, they say we don't have the we didn't compare the experimental data and the theoretical data, but actually we did it in every chart of our report. And also we discussed the contact point. And in my opinion, like if you want to reach the terminal velocity, it should have and it must have 2 contact point. Even if you only have 1 contact point at first, it will have 2 at when you reach the terminal velocity. And about the inclination angle, since the whole system between the ring reaches the terminal velocity, it's unstable, so we can't measure it. And so the measurement that we shown on our PowerPoint is the inclination angle at the terminal velocity, since it would remain stable. And the reviewer says that there's a big, our experimental data didn't fit our theoretical data, and so we did a modification, which is the sighting motion, and this is the end of my summary of my remark.
All right, here comes the question from jurors. Please take the floor, both of you. Questions from yes.
I have a question to 3 of you. All of you mentioned about the friction and what happens if you change the material of the washer. For example, I think you use rubber washer. Is that right?
Yes.
What if you use a more slippery material like the metal or something else?
I think changing the material will affect the kinetic friction, and will also it affects the terminal velocity. Huh?
How? Larger or smaller?
It depends on the material that we changes.
More slippery material.
More slippery, I think it will the time to reach the terminal velocity will be shorter.
I think the torque of friction and the torque of gravity should be balanced so that it could reach the terminal velocity. So I think friction is necessary in this experiment.
But then, how would you change it if you decrease the friction? If you change the material like the metal metallic?
I think if the friction is smaller, then it should spin faster, so they could have the same friction to balance with the force from gravity.
I think when I change the material into the more when I change the material, there will be more they will cause the waves change. So I think because the friction need to resist the gravitation, so I think they will change the terminal velocity. If the water become heavier and heavier, and we need the more friction to resist the gravitation to arrive the terminal velocity.
So how will it change? I mean, will it the terminal velocity larger or smaller?
We need larger friction to resist the larger gravitation. When you change the material, you will get the change of the
What change?
mass.
What change?
Wait.
No.
Mass.
All right. Okay, I think we'll move on to the second question. I got a question for the reporter. Could you take to the conclusion?
Okay.
You have a formula for the terminal velocity.
You mean the
In
after we
conclusion
modify
part,
it?
yeah. You have an equation for the terminal velocity.
Yeah. No, 这个。This one?
No, not yet.
不放。
No, this terminal velocity formula in the end, in the conclusion part.
Conclusion part? Okay.
Yeah, this is one. Yeah, the first one. Which parameter related to the friction? Is there any friction related?
No.
You know, no. Then how are you gonna?
Can you repeat your question?
No, I'm asking in the formula which parameter related to the friction? I mean, you have cosine, you have R1, R2, which is our geometric number. I don't see any coefficient of friction whatsoever. Right? All right, that's fine. That's fine. So any more questions? Well, final question, short question. For given the ring and rod, if you change the diameter, are they going to reach to terminal velocity no matter what? Start from you. Even you have a larger washer, small washer, whatever, it's going to always reach to terminal velocity?
I think it will.
Okay. You?
I think it will affect.
In what way? I mean, are they going to always reach to terminal velocity?
I think
Yes or no?
yes.
Okay.
I think the key point is the friction. If the friction is enough, they will get the terminal velocity.
Okay.
And the roughness of the rod or the wetness of the rod, and they will.
Okay. Yeah, great. Thank you. So here comes the scoring time. All right, show your score for the reporter. Start from me. 5, 6, 6, 6, and 7. Here comes the score for the opponent. Yeah, there's your score. 5, 6, 5, 5, 5. Now comes to the score for reviewer. Please press your score. 5, 5, 6, 5, 5. I think pretty much even. Right? So we're going to take a break for 10 minutes? 10 minutes. Okay, 10 minutes. Thank you. This one, the problem has been chosen to be number 10. 10 droplet explosion. So we're going to go into the operation for the order for 5 minutes. Oh yeah, please write out a representative of your team on the platform. You're going to start it? Okay. All right, good.
Hello everyone, my name is Wenming Han. I'm the reporter from Team Vision. Today I'm going to report to you problem number 10, droplet explosion. First, the problem is about investigating and analyzing the fragmentation of water mixture droplets is deposited on a hydrophobic liquid. The water mixture is made of water, isopropyl, and ethanol, and we use sunflower oil as the hydrophobic liquid. My report includes the experimental observation based on the water mixture concentrations, the droplet size formed by the marangoni burst, and the temperature change due to the evaporation of isopropyl and ethanol. They analyze the data according to the previously mentioned parameters, and finally a brief conclusion. Table 1 lists the surface tension of different liquids. The surface tension of water is much higher than surface tension of sunflower oil, so it will remain 1 drop when it is deposited on the oil surface. But the surface tension will be lower when water mixed with isopropyl and cause 2 drops to diffuse. And as you can see, the volatilization of isopropyl and the ethanol will cause a surface tension gradient during the diffusion process. And the endothermic reaction of isopropyl volatilization will lower the surface temperature of the solution. The surface tension and the volatilization are important factors that affect the marangoni force. The expansion coefficient S is expressed in terms of tangents.
in which surface tension between oil and air tries to pull the liquid out, while the surface tension between the liquid and the oil tries to pull the liquid in. When S is greater than 0, means the liquid will expand and stop expanding when S is 0. The liquid drop shrinks when S is negative. This is the diffusion patterns of 80 and 70% isopropyl mixture. So that after 15 seconds of deposition, 80% isopropyl expands faster than 70% and creates more but smaller fragment droplets on the edge of the circle. And the 60 and 50% isopropyl diffusion patterns show the same trend with 50% isopropyl mixture expands the least but with largest fragment droplets on the edge of the circle. So from page 6 to 7, we see that all mixture droplets expand right after they are deposited, which means the expansion coefficient S are positive for all 50 to 80% of isopropyl. However, as the droplets diffuse, isopropyl begin to volatilize, so that the concentrations drop and the surface tension increase until S equals 0. The droplets stop expanding, but the following volatilization further increase the surface tension, making S negative and causing spontaneous self-accumulation. We can see that volatilization is a key factor to the expansion coefficient S. This is a closer look at the diffusion patterns. A clear view of outer and the inner circle of isopropyl. And this is the picture after the volatilization. It shows the final stationary state of the diffusion patterns, and all droplets exploded into tiny droplets. The lowest isopropyl concentration gave the largest size of final droplets. And we also measure the surface tension of mixture concentration, and it drops rapidly as the concentration increases. For any given concentration, the surface tension of ethanol is greater than that of isopropyl. The figure shows the evolution of droplet size for 50 to 80% isopropyl mixtures. Both radius of outer inner circle increased after deposition on the oil surface, but the inner circle starts to shrink as the outer circle stops expanding, and half isopropyl concentration produces the largest diffusion circle. But for the diameter of the ethanol, you can see that the maximum of all concentrations of the maximum diameters of all concentrations of ethanol are smaller than that of isopropyl, and that is because the expansion coefficient S of isopropyl is bigger than that of ethanol. And also you can see the outer ring of the ethanol will shrink after 20 to 30 seconds, but the isopropyl won't shrink. So in the next page, I will discuss why this happened. And we think since the viscosity of isopropyl is higher than that of ethanol, we speculate that the outer ring of ethanol experiences less viscous resistance and shrinks. And since the volatility of isopropyl is lower than that of ethanol, the surface tension of isopropyl rises lower than that of ethanol. So we speculate that the surface tension of isopropyl is not enough to resist the viscous force, and it fuses with oil to form a stable droplet without shrinking. And the figure shows the expanded space of the outer and the inner circle of isopropyl. You can see that the outer ring of all concentrations will gradually form constant velocity. After expanding for 5 to 10 seconds, we think that as the isopropyl evaporates, the thickness of the droplets will become thinner, and the surface tension will increase, which will cause the total force of gamma LV and gamma OL becomes larger, and then offsets with gamma OV to form the constant velocity motion. And this is the droplet expansion space for ethanol. And you can see the expanded speeds for both mixture drop rapidly after it is deposited. And this is because the volatilization leaves more water in the droplets, so increases the surface tension. Also, in these two charts, you can see the velocity of expanding out quickly in the first 5 to 10 seconds. We think this is related to viscosity, as you can see the formula here. The higher surface gradient will lead to the higher viscous stress. So it will let the shrinkage become constant velocity motion after 5 to 10 seconds. This graph shows the droplet size and the number of isopropanol and ethanol at different concentrations. The formula fully explained why when isopropanol exceeds 50%, the surface tension will become too small and resulting in smaller wavelengths and such smaller droplets. And besides, we know that the isopropanol has less density than ethanol, and such it will, and also isopropanol that has less surface tension than ethanol at every concentration. So this results in smaller wavelength and such smaller droplets. During the diffusion process of the droplet, the temperature gradient will change due to the volatilization of the isopropanol components. Figure 3 shows the temperature distribution over time except for the higher concentration solution, 80 and 70% in the early stage of the diffusion. The volatile components are concentrating in the center of the droplets. So the temperature is the lowest, and the rest are the lowest temperature at the edge of the droplets. And this is because the thickness of the diffusion edge of the droplet is the thinnest. So isopropanol will evaporate the most. So we think the surface tension will change with the temperature. We think the surface tension is high where the temperature is low, and the surface tension is low where the temperature is high. And we have 2 points for the test 2 cases. The lowest temperature is the edge of the droplets. And because the thickness of the diffusion edge of the droplet is the thinnest, isopropanol and the ethanol evaporates the most. And also the thickness of the droplet is also related to the contact angle between gamma OL and the gamma OLV. And the smaller the contact angle, the bigger the force of shrinking, and the smaller the expansion coefficient is. And here comes our brief conclusion. At first, the surface tension of the mixture droplets is weaker than the adhesive tension to the oil. The droplets expand, but alcohol keeps volatilizing as the droplets expand since the edge is thinner. Alcohol concentration drops faster, so this increases the surface tension, eventually stops the droplets from further expanding and causing the edge to break into smaller fragments. And this is what we call droplet explosion. Then stronger volatilization occurs in the larger fragments, lowers the temperature, and creates larger surface tension and pulls in nearby smaller fragments. And finally, you can see a lot of stable droplets on the oil surface. And we guess that is because the isopropanol and the ethanol all evaporates completely, and only leave water to form the stable droplets on the oil surface. Thank you for listening.
All right. Here comes a question from the woman.
Please turn to the page of the size of the final droplet. The page of the final droplet. This size.
Wait.
Yes. Can you tell me what the unit you use?
We use pixel. We use image data to analyze our
So
data.
1 pixel is how many centimeter or millimeter?
Pixel is very small.
So how many or you didn't quantification?
We just use pixel to represent our units.
So you didn't measure its real depth.
Yeah.
Then Have you have any control variables?
Well, repeat
Have
it
you
again.
have any control variables?
Control
Variables.
like what? Control variable like what?
Like the value of the liquid or the humidity.
We drop 50 ml of the droplet, and also we use 0.2 centimeters of thickness of oil.
Okay. Now have you controlled the humidity?
Yes, we also control the humidity. We have mentioned it there. The humidity is 72%.
How do you
When-
control it?
How do I control it? We do this experiment at the room humidity, and yeah, it's just 72.
Okay. The question is.
Excuse me, time's up. Preparation time of the opponent for 3 minutes. Opponent, you will take the floor for up to 4 minutes before proceeding to discussion with opponent.
Question 10, droplet explosion. This is a problem statement. Use a water mixture to a space of the hydrophobic liquid. It will sometimes have some fragments. But investigate the parameters that affect the fragmentation and the size of the final droplets. These are all summary. The theory reporter says is that the surface tangent decided diffusion or shrink, and the volatilization will change the surface tangent. So when it diffusion to a side, it will shrink. This is the experiment. Their control variables is humidity and volume, and their independent variables are ratio, isopropyl or ethanol, and temperature. And their dependent variables is the droplet size. Their conclusion is droplets expand because the surface tangent is smaller than the tangent tangent, and is bigger than the tangent tangent, and the droplet edge is thinner. Okay. This is our suggestion. The advantage is the clear figure of experiments, clear data and charts, and consider many situations. But we suggest that their units are clear.
We're going to move on to discussion.
Yes.
All right. You ready to begin?
The question statement says that we need to investigate the parameter that will influence the final drop. But I didn't see that you compare how it will influence the size of the final drop.
Yes, our problem is the different surface tension, the different liquids, and also the temperature change by the temperature, and that is the parameters that affect this experiment.
There is a Marangoni first. Did you
Yeah.
talk about it?
Yeah, the Marangoni means the deep surface gradients caused by the temperature change of the surface of the oil. Yeah.
So if the ratio of the ethanol or acetanol, the size will be small or be bigger.
The ratio of the
Ethanol
ethanol and the what
and the propane.
as a problem.
Will it the size will be bigger or be small? You can compare
You mean
the
final
final
droplet?
size.
The
Yeah.
final droplet
Yes.
size? Okay. And the average size of each droplet is this. Ethanol is bigger than isopropanol, and I just mentioned that because the isopropanol's density is less than ethanol, and also the isopropanol's surface tension is lower than ethanol's in every concentration, so it will lead to the smaller wavelength. And I want to mention that the smaller wavelength is that the droplets will become like this in the edge of the circle, and this is the lambda c is the smaller wavelength. So we have seen that the smaller wave will cause to the smaller droplets, and that's why I use this formula.
Have you calculated the surface tangent and the tangent? Because maybe if the number will be too big or too small and
Yes.
didn't influence.
We have measured the surface tension in every concentration, like isopropanol and ethanol, and we see that the surface tension of ethanol is bigger than isopropanol as every concentration.
Have you calculated the power of the surface tangent?
The power of the surface tension,
Yes. Because
the power of the surface tension. Let me explain how surface tension works in this. So let me explain how surface tension works on this experiment. Like, this is, may I use the blackboard?
Sure, go ahead.
This is the droplets. And this is the surface tension between the air and the oil. So when we drop the isopropanol mixture, and the total tangent of the This is the surface tension between the liquid and oil, and this is the surface tension between the liquid and the vapor, and the total surface tension will become smaller, and this will bigger, and this will pull the liquid out. So that's why it's explosion.
So have you calculated the relative relationship of the surface tension and the final drop size?
And we have found that the bigger ethanol concentration has the bigger number of the droplets, and that is because like the surface tension of water is very big, right? So it will, when we drop the water on the oil surface, it will only remain one droplet on the oil surface. So we think the lower the surface tension, the more the droplets, the more the number of droplets, and that is because the lower the surface tension, and the attractions of the molecules is smaller, so it will explode more droplets. Yeah.
Pay attention to the temperature.
Turn to the what?
The temperature page.
Temperature change, like this.
You control the temperature. You control the oil temperature.
Oh yeah, we control the temperature as the room temperature 22.
The temperature is 22.
Yeah.
And the
And we see
oil
that.
temperature is 80 or 70.
What?
So you control have you controlled the liquid temperature or you control the oil?
We have measured the liquid temperature, and the liquid temperature of oil and isopropanol and the ethanol are all the same as the room temperature 22. Yeah. And 80 and 70 means the percent of the mixture. And I'm sorry I didn't mention that. And also we have seen the lowest temperature is concentrated at the center of the circle. And that is because when we drop the isopropanol to the oil surface, and the volatile components are all concentrated in the center of the droplet, and it will absorb the heat of the oil surface and make the temperature become lower. But as you can see, as the time passes, the lowest temperature will go to the edge of the circle, and this is because we think that the thickness of the edge of the circle is thinner, and that's why we think that the edge of the circle evaporates the most, and it will give a big force of it. When it becomes thinner, the contact angle of this and this will become smaller, and it will shrinking, give a force of shrinking, and why this is also related to shrinking.
Can you check your theory page?
Theory page. You mean what theory? Oh, this one? Okay.
Yes.
The front. This. Front. This. Front. This.
Yes. You say that the water and the ethanol or the isopropanol mixture will make their surface tension down, so it will diffuse. And if today we choose 80% of isopropanol, while its surface tension smaller than the sunflower oil's surface tension,
Yes, so
it would count it. I don't think it was. This surface tension is smaller than the sunflower oil's tension.
what? I mean, we mix isopropanol and the water, and so the total surface tension of the mixture is totally smaller than sunflower. Sunflower. I know what you
The
mean.
water mixture, not the ethanol or isopropanol.
The water mixture,
Yes. If you choose the 8% or 70%.
8%, 80%
80%
of
or 70%.
mixture, and
Yes. And its surface tension will bigger than the sunflower oil, but in your experiment, they will still diffuse.
it will bigger than the surface tension of oil.
But it's still diffusion. But
Yeah, no, it won't be bigger than surface tension of oil.
Yes.
Why do you think the surface tension of mixture will be bigger than oil? Well, the isopropanol's percentage is much bigger than water.
You can carry on? You done? Okay. You make a summary for 1 minute. You summarize for 1 minute. Conan?
No, we have discussed.
Conan, you need to summarize in 1 minute.
Should I pause it, the talk?
That sounds good.
We're discussing about that the lower surface tension may make final droplet size bigger, and the temperature of the droplet concentrate on the center of the droplet.
What's that? All right. Okay. Comes to the question from reviewer to reporter and opponent for 3 minutes.
First of all, I want to ask the reporter, where are your equipments? Do you have the individual page for that?
Individual
Page for your equipment?
No, but we use pipette to drop our water mixture.
Okay. So, and what software do you use to analyze the data? I mean the size of final droplets?
We use ImageJet.
Okay. And how do you define final?
We define final as the like this picture. It is the picture of or after the volatilization, and then it will become stable.
So where do you think is the final?
It is final.
All of them is final?
Yeah.
So
it's final droplets.
You define final as after all of the evaporation?
Yeah. Oh, yeah.
Okay. So how do you define or quantify the hydrophobic and lipophilic in the current state? Because that will relate to the liquid you choose to do the experiments. How do you define or quantify the hydrophobic and the lipophilic?
So we just use hydrophobic as the sunflower oil, and we didn't use another liquid. Yeah.
And how do you know it's hydrophobic? Do you have some theory to quantify that? No. Okay. And what do you think is the factor that influence these experiments the most? What parameter do you think affects the most? Parameter. For example, the temperature or the volume they dripped.
I think it's the ratio.
The ratio, the concentration.
Is there right? I think it was the ratio.
Okay. And for the reporter, do you consider the evaporation as a major parameter?
Major parameters.
Do you think so?
We think surface tension is the major parameters.
Okay. And what do you think about the evaporation? Do you think the evaporation is a major parameter? Okay. Next question. How do you think is the marine effect is going to affect the phenomenon the most? What do you think the marine effect is? What it do? What's the most important thing that the marine effect contribute to this experiment?
Marangoni effect is just a noun to explain how the evaporation influence the surface gradients of the mixture, water mixture. Like I just showed in this picture, like the noise.
Next question. Okay, so Do you have error bars in your graphics about the size of final droplets? Do you have error bars?
No, it's all.
Excuse me, hands up. Preparation time of the reviewer for 2 minutes. Reviewer, your time for 4 minutes.
Good afternoon, everyone. I'm a reviewer from the team Typt. And today, the topic I'm going to review is the question 10, the droplet explosion. This is a problem statement, and we think the main focus should be on the hydrophobic, the fragmentation, and the final. Overview of the reporter and the advantage, including substantial diagrams, clear thought, and make the initial conditions the same. And she's trying to eliminate the deviation. And our suggestion for her is that she is without equipment individual page and their setup. And second one is that they fail to make sure that every pixel has the same area. And third one is that they fail to notice the characteristic of ethanol and IPA. It's because that they are both lipophilic and hydrophilic at the same time. And the fourth one is the spreading coefficient derivation is not clear enough. And the last one is that other charts is without error bar. So maybe we can think that they didn't do much experiment about it, so that they don't have an error bar. An overview of the opponent, his advantage including structural suggestions and good time management. And our suggestion for him is that he can have deeper discussion. And discussion 1. The opponent asks, will the ratio of the ethanol and IPA affect the results? The reporter say that due to the density of the surface tension, so that it will affect. And the opponent asks that, have you calculated the surface tensions? The reporter says yes. The opponent asks, how surface tensions affect the experiment? The reporter answers, the droplet will be dragged out by the larger surface tensions, which is the Meringian effect will contribute to the experiment. And discussion 2. Opponent asks, why the sizes varies from the concentrations? And reporter answers, related to where the thinnest part of the system and the chance of evaporating, so that the sizes will vary from the concentrations. And the opponent asks that, why the sunflower oil surface tensions is smaller than the water mixture? The reporter answers, it should be between the two liquids, so that the concentration should be between the two. And here are some missing points. I think they could have further discussion. The first one, we highly doubt the accuracy of the size of final droplets because from their experimental demonstration graphics, I didn't see the architect scale, and they didn't mention the analysis parameters at first. And the second one, we are curious about the initial motivation of the mixture spreading. because other reviewers think that it is a work of adhesion work. Because reviewer believes that it is the work of adhesion minus the work of cohesion in the system. So this is why the spreading coefficient S is the rift. And the third one, she has talked about the Young equation, so that we think that the Young Laplace equation, and the gamma here stands for the coefficient of surface tensions. And this one will also affect the experiment. And probably she could do more research on it. And number 4, reviewer believes that the HLB value, which is a lipophilic balance value, is how you quantify the hydrophobic, lipophilic at the same time. So that this is why we choose the IDA, the ethanol, to do the experiments. And okay, but she failed to mention about it. And next one, she didn't talk about the parameters that easily to come to mind. For example, the angle you drip the mixture and the degree of solution mixing. And the last one is the error bar I just mentioned about. And
Excuse me, hands up.
thank you.
Here comes concluding remarks from the reporter for 2 minutes.
First of all, we have done many experiments, but we choose the most accurate experiments to analyze our data. And also, we have discussed the Marangoni first thing. And the Marangoni first thing is just now to represent how the temperature affects the surface gradient of the water mixture. And also, the parameters of our experiment is about different concentrations of liquids and also different surface tension, and also different surface tension between the different liquids. And we also see how lowest temperature affects the evaporation and how it affects the spreading and the shrinking of the water mixture. And also, we think that the hydrophobic liquid means the liquids won't fill with water, so we choose oil to do our experiments. And also the angle of how we drop the mixture is just vertically drop it and at random heights and the random height. And we think the height won't affect the experiment. And this is the end of my concluding remark.
All right, thank you. So here comes the questions from jurors. Question? Yeah, yes, please.
Can you what parameter can you choose to increase the amount of small droplet obtained in the end? Can you and say what parameter and why is that?
Okay.
Maybe more intuitively, and if you want to increase the amount of droplet obtained, what will you do?
What will increase the number of droplets?
Yeah.
Oh, yeah, because the higher the concentrations of the ethanol solution, and the lower the surface tension, and so like the attraction of the molecule of the liquid will become smaller, so it will burst into the more droplets.
Well, what if you use up to say 99%? How is it going to happen? If you increase up to 99%, is the number going to,
Well, we have used the 99%, but we found that the speed of the evaporation is just too fast. So it is not good to our experiment, so the phenomenon becomes not so clear as the 95% because it evaporates too fast.
So there's an optimal value, right? Optimal, the best one. The best value to have the highest number of droplets.
Yeah.
What is the number?
What is the number? We think 95% is the number, is the best number too.
Okay. All right. Any more questions?
How about
Yeah.
other group?
All right.
I personally think that The first one is the volume, because the more volume you drip, the more small droplets you will get. And the second one is that between certain area of the concentration, the higher it is, the more droplets you can get. As for the question the professor just asked, I think that when it's up to 99%, I think the mixture will immediately dissolve in the oil, because the lipophilicity of the mixture is make the whole mixture become a lipophilic drop as well, so that it will dissolve in the oil immediately.
All right, thank you. The opponent, you can say something based on the question asked. No, that's fine. That's fine. Any more questions? Could you turn to page 11? 11. Yes. You did experiment. This is your data, or you copied it from others?
On our data, we use the machine to measure the when we draw the
No, I'm asking you did the experiment.
to measure
All this data.
the surface tension.
Surface tension, yeah. You carry out experiment, or you copied it from other papers?
Oh, we have done the experiments, but we also see
So let me ask. If you look at the concentration of zero,
of the euro.
yeah,
Yeah.
on the left-hand side, it's going to be much higher than the one on the right-hand side, right? Because if you see the tendency, okay? If you see the tendency for zero, it's going to go to, way high.
Yeah, the little because it has only water. No,
Yeah, but how about on the right-hand side? I mean, it's less than 70.
like
Yeah.
less than
Even the
70
experimental
point.
data,
It's higher than
Even-
70.
is there any, you don't see any questions here?
Isopropyl and ethanol is different.
That's right, but for zero concentration, the all water,
Water,
right?
but you have two
Oh, yeah,
different,
that's my mistake.
Why it gives you different number?
different data point.
Probably because the angle we measure is just round to yes. Just
So that's another parameter.
Yeah.
All right, okay. Okay. Yeah, I think it's good to, yeah. All right, scoring time. Ready? All right, the score for reporter, 7, 6, 7, 8, and 6. Here comes the score for opponent. Start from me, 5, 5, 5, 5, and 4. Comes to reviewer. All right, start from me, 7, 7, 7, 7, and 8. All right, pretty much even. So we're going to take 10 minutes break. All right. Should we begin? All right. So the problem has been chosen to be number 7, 3-sided dice. Reporter, you have 5 minutes to prepare your presentation. So you can, start anytime you like. Before you start it, please write down the representative's name on the blackboard. You guys started? All right, you may begin.
Hello everyone, I'm the reporter of Team Yellow, and now I'm going to report question 7, three-sided dice. So the problem statement. The question is how to make a cylindrical dice that it has the same probability to land on its side and one of its faces. And first, we need to know that solid angle is the angle of an object to a specific point in three-dimensional space, and it can be considered an analogy of an angle in three-dimensional space. So this is the formula, and the solid angle of a sphere is 4 pi, when theta equals 2 pi. So we need to suppose the ground is viscosity infinity, and the dice sticks to the ground after it hits it. And then we can pose three lemma. First, the probability of each face is equal to the solid angle of the face divided by 4 pi. Second, different dice have the same probability as long as the solid angle is the same. Third, the sum of the probabilities of all faces is equal to 1. So here is our derivation process. Look at this 6-corner prism. We define the distance between. We define the distance between the vertices to the center is A, and the height is B. In a n-corner prism, regular n-corner prism, and we can find that the solid angle which B1, C, B2 is this, and here is the, so this is the probability that the n-corner prism lands on the face is. So what is face? We need to go back to this. We define the top and the bottom is face, and the other faces we call it side. In the following presentation, and the cylinder can be regarded as a positive n-corner prism when n tends to infinity. Let the radius of the face be 1, the height be b, and the probability of one of the faces touching to the ground is half minus b over 2 times root of 4 plus b squared. So look at this picture, and when the ratio of column height to radius is root 2 to 2, it has the same probability to land on its side and one of its faces. So here is our experiment. We use $10, and its radius is 30 millimeters. Its thickness is 1.9 millimeter per coin, and we use clay to connect the coins together. So here is our experiment procedure. We want to simulate the real situation of coin passing on the floor. So in a real situation, the floor isn't smooth and the coin bounces a few times before it stops. And we combine 4 to 8 coins into a cylinder with clay. Each factor conducts 50 times. Here is the video. And next is our data. And here you can see the face means the average of the front and the back. And we use linear regression to make this chart. We can find that when the radius of column height to radius increases, the average probability of one of the phase decreases. So here is our summary. The region of the dice in the real situation is bigger than the ideal situation. And here, A means is the theoretical situation when the radius is 0.7 and it is the approximately of root 2 to 2, and in real situation the radius is 10 to 1. So here is our reference, and thank you for your listening.
You done? No. Okay. Question from opponent for 2 minutes.
Okay, since I would ask what's the certain parameters of this experiment. What is your parameters?
Oh. It means what?
Okay. Since you put a lot of coins together, right? And how do you think the mass is evenly spread? Like the mass. Since you have put the plate between it, how do you think the mass is evenly spread? And if it's not evenly spread, how did it fit your?
Because our theory is in a ideal situation. So in this situation, the viscosity of the ground is infinity. Therefore, the mass won't influence the result. Actually, in the real
Did you have the theoretical data chart or the line that you calculate? The theoretical
no.
from the formula.
Theoretical of the formula.
Theoretical data that you. Okay, it's okay. Next question. Did you release the dice from the same height, or did you?
No, we didn't consider any.
Or it's okay. And how do you think that?
Excuse me. Preparation time for 3 minutes.
开始讲吧。
One may take the floor for up to 4 minutes before proceeding to discussion.
Okay, hello everyone. I'm the opponent from the MD Fresh, and our topic is three-sided dice. And first of all, and about the theory, the opponent used the geometrical characteristics to explain. But actually, according to your problem statement, you must have the physical characteristic and the geometrical characteristic. But in their report, they only have the geometrical characteristic, which I think it didn't match the problem statement. But I did have a clear explanation of a theory. And about their experiment setup, they didn't control the height of the when I throw the dice down, and and the system have the parameters in their experiment. And our advantage to them is that they can do the experiment more complete and you. Yeah. And about the advantage of the setup is that we can see clearly in the demonstration. But our suggestions is that they don't have the theoretical simulation and didn't control the height of the lacking of the dice, which I just mentioned before. And about the theory, the formula is quite completed, and they did calculate the ratio between the height and the radius. And our suggestions is that they have to explain more about the parameters and the solid angle. And also, their theory didn't match their experiment, but they didn't explain but they didn't modify it. And our suggestions is that they didn't have a clearly shown. They didn't clearly show their experimental data. And here comes the discussion. So,
All right. Reporter, take the floor, please.
okay, since your model is unevenly, the mass of the model is unevenly spread, how do you think it would affect your experiment?
In our experiment, I think first you say the mass, and I think because we use clay to connect the coin, and coin is not a perfect shape of the cylinder, so it may make the mass is not really.
It's uneven. So how do you think it would affect your experiment?
Experiment.
Like you have different layers, and how do it affect?
Okay.
According to your experimental data.
First, I think when the cylinder drop to the ground in a floor, it will bounce. So.
Okay, it's okay. From your report, what I only see is that you did calculate the ratio between the radius and the height, but I didn't see the parameters that you changed. Or what do you think if you change the radius to 2 or 0.4?
We only change the radius in sorry. Show me the.
So
We only change the radial of column height to radius, and it's the only parameter we keep.
So I think in the future, maybe you can consider the different mass or the different radius of the streetcar dice. And how, since you don't have this physical characteristic of your experiment, and how do you think and how do you explain? And how do you explain in a physical characteristic of your experiment?
So in my experiment, I think you said I only use theoretical experiment, no physics, but in theory, physics didn't affect this situation.
No, but the problem statement told you to do so. So you didn't do it.
So sorry, I can't.
I mean, the problem statement told you to do the physical characteristic, but you didn't do it. And since you say the viscosity of the surface is infinity, right? And then how do you define that if the dice, if this is a floor, and if this is a dice, and it's like this, how do you think if it's like this? How do you think it is full or it's full? How do you think this one related to the side or the face?
We suppose the center of the mass is here, so in the center of the cylindry. So that when the face of the solid angle of face or the solid angle of side touch the ground first, it will use this chain to start there.
I mean that the surface viscosity is infinity. So and each side of dice is 1/3. And if in this case, how do you think this in this case is related to the size or the side or the face in this case?
I don't think the size will affect the.
No, I mean since your surface viscosity is infinity. So in this case, how do you define that the surface that it touches the floor is the side or the face?
What did you say? How do I define that? Whether here drop to the ground and it will.
Yeah.
I just use gel for the solid angle of it, like.
No, I think this is nothing about the solid angle. And in my opinion, I think you can use the potential energy to measure this. If the potential energy is bigger than value, it's bigger than the value, and you can consider it as the side. And if it's lower than value, you can consider it as the face. Do you think it's correct? Yes. Since this in this model and this model, their potential energy will be different. And so, did you do the experiment in reality? Since I only see the simulation in your experiment, but I didn't see the real reality.
The data there in that chart is the experience.
Oh, okay. I'm sorry, it's my fault. And you say in the reality it's 1/10, and by the theoretical data is root 2 to 2. And since there are big gap and big differences between them, how do you explain this
Sorry,
phenomenon?
1 to 10 is actually.
1 to 1, and it's still a big gap since it's about 0.7 to 1. And how do you explain the differences between them?
I think, first, I think the mass distribution is blue and split. And third, we use we use smooth floor instead of the tower to make it more controllable, but it may bounce and make the
But your experiment setup is that the surface viscosity is infinity, so it won't bounce in your experiment. And so you can use this point to explain this phenomenon.
and we can reach this.
So I think next time maybe you can just and you can still consider surface instead of just make its viscosity as infinity. And another one is in your experimental setup. I see that there's $50 and $10 coin. And how do you see it was different?
Sorry, we only use $10 coins.
And
in my program.
And how do you think the mass will affect the probability?
I think when the center of mass is not really in an ideal situation, so
I mean the mass, like 5 gram, 10 gram. Yeah. Okay, as for me, I think that if the mass is bigger, it will increases the coefficient of restitution. That means it will bounce more, and that may affect the result. Yes, if we consider rebouncing, since this setup is totally unreasonable, the viscosity is even. And how do you control the heights if you only use $10? The point of $10.
We control height actually we use so just like the video we just measure it and show it, but maybe there are small, but I don't think it will affect it.
And also since your system is not customized, so how do you think your setup is accurate, like the height, the ratio between the radius and the height, and also the clay must have a strong viscosity. And how do you think it will affect the coefficient of restitution?
When the height is bigger, maybe it will bounce for more time. So.
No, I mean, how do you think your setup is accurate? Since since your setup is not customized, so it may have a big error between what you think and it's actually at. So actually, as for me, I think that it won't be accurate. So perhaps you can use a 3D printer to modify the experiment. And also about the clay one, the viscosity one. How do you think?
I will try that.
Okay.
In the future.
And also, at the same time, as for me, I think that the viscosity of the clay will affect the coefficient of restitution. So it may that the dice bounce lesser, and it will definitely affect the experiment. And I think it would be a strand data, which will definitely didn't fit your theoretical data.
But now we have no, we are not.
Okay, that's just the end.
All right, so I'm going to summarize the discussion in 1 minute.
Okay, in our discussion, we found out that according to our problem statement, the reporter has to have the physical and the geometrical characteristics about the experiment, but they only did the geometrical one, which doesn't match the current statement. And also, if their setup is the clay and the coin, you can accurate to the ratio between the radius and the height isn't accurate. And also, the viscosity of the clay might affect the result. And also, the setup of the surface viscosity, which they think is infinity, isn't reasonable. Since if a model is like that, how do you define that? Is the side that touches the floor or the face that touches the floor? So, and this is the end of my summary. Thank you.
All right, thank you. Question from reviewer to reporter, and comment for 3 minutes.
Thanks for reporting on the opinion. And my first question is for the reporting. What do you think what caused the dice turn?
What caused the dice turn?
What?
I think it's the gravity caused the dice turn.
Okay, correct. And for operating.
And as for me, and that's what I just mentioned, I think it's the coefficient of the restitution, which is the rebouncing. And if we expand this phenomenon using the potential energy, if the potential energy is bigger than it is when it's stable, it will keep rebouncing.
Can I take my question? Do you think which is the natural parameters that affect the result?
I think the materiality is the point that it
The contact term. It could mean the contact term.
it is counterpoint.
Yes, okay. I'm free of winning. The natural parameter that affect the result.
I think that the ratio between the height and the radius will affect, and also the material of the setup. So
sorry, your question is about what parameter change, or you ask the same dices or different dices?
can I get?
Excuse me, listen to the reviewer, please.
Do you think the material of the surface will affect the result?
In real world?
Yes or no?
Yes.
The material of the surface.
I think also, I think they should draw a 3D model of it. I think it will affect, so I think they should draw it.
And then, next question is, if the thickness of the dice is very thin, like close to 0, and what will happen?
Close to 0.
Yes, the thickness close to 0.
I
Maybe upon the first.
And which close to 0,
If
actually.
the thickness of the dice is very small, like close to 0.
I think the probability of the face that touches the ground will equal to 1, or almost equals to 1.
Wait, important?
I think so, yes. I agree with that.
Okay. Thank you.
All right, preparation of the review for 2 minutes. All right, review your time for 4 minutes.
The presence of one on reviewer sheet from condition, I'm gonna to review problem number 7 result design. As a problem statement C, we should land a coin in a real object and what is the physical and geometrical characteristics of a cylindrical die so that it has the same probability to land on that side and one of its faces. And I want to mainly focus on what's the dimension of a very cylindrical dice and the physical characteristics of the dice. And its overview of the reported and their observation shows the video and analysis they use the solid angle and in their experiment the parameter is the thickness to diameter ratio of the dice and my reviewer have some suggestion they can do more parameters and their experiment dice, something like the material of the contact surface or the releasing height raising angle or the mass of the dice or the position of the center of the mass of the dice, and I think that would affect the result in the real situation. And this is an overview of the opinion. They have brief overview of the presentation, and they discuss the friction and the coefficient of restitution, and their advantage has a good time management. And as a discussion, I asked if the thickness of the dice very close to 0 and what will happen, reported just agree with opinion, and opinion C, the probability of landing on feet might be 1, and I think if the thickness is very close to 0 and it will become a surface, and then it would not be the three-sided dice. So I think the correlation between the thickness and the probability would not end the correlation in this instrument limit. And this is a material of the contact surface will have the result and the operator says yes and opponent says yes. And in my opinion, yes, the coefficient of restitution would be different, and the reaction force to the dice would not be uniform. So it will affect the result. And I asked what make the dice stream. The opponent say the gravity, opponent say the coefficient of restitution of the collision. And reviewer believe that the torque from the normal force when the dice hit the ground and the weight are which make the dice stream. And opponent asked what's your physical characteristic in your experiment, and the operator didn't do the experiment, and opponent that talked about the potential energy. And I think yes, the potential energy is the physical characteristic in this problem. And there's some missing point. First, the center of mass would affect the result because the center of mass, if the center of mass change, the very center will change, and the direction of the dice is related to the relative position of the very center at the contact point. And thank you.
Concluding remarks from reporter for 2 minutes. Reporter,
Okay, as for the remark of I so by the solid angle, we know that the line from the center to the front is vertical, and it can stand for the bending side it shows. So which solid angle constant? The mass affect the bouncing situation, but it won't affect the last contact of the dice. So if it won't affect the result of the situation, that is quantity is infinite. And in the chart, the relating efficient of the experiment are high, and it shows the mass difference doesn't affect the accuracy as much as the opponent's opinion. And the three side means top, bottom, and side, and we use faces instead of top and bottom. And air resistance are average on the surface, so I think it won't affect. Also, you say we didn't consider the mass, but in our model, the center of mass is the reason why it will get to that. It will get in that side. Yes, thank you for.
You done?
Yes.
All right, great, thank you. Here comes question from Cheryl. Any questions? Let me start with the report. You have the data of the probability versus the aspect ratio. The data, yeah, this one. Three of you, did you see any problems with this data? Start from Ottoman. Did you see any problems with this data?
There are the unit.
Other than that?
They don't have the error bar in the unit.
Other than that?
Other than that, the second point, the second data is unreasonable. It should be upward trend line.
Okay, reviewers, do you see any problems? Reporter, you want to go first?
We didn't do enough times of experience, so.
You didn't do that?
So we
where
only
you got
do
this
50
from?
times, so the data in real.
Okay, that's fine.
Can I add a little bit?
Yeah.
Since the line is by the simulation, so I think if it's
What simulation? This is just real data.
it's a real data.
The real data.
But
Let me put it this way. What if the aspect ratio is 0? Meaning that the high is, 0, say, approach to 0. What would happen? You want to answer? Sure.
The trend line is the x squared. The trend line he used is the x squared. It's
What's
curve.
that?
It's a curve.
So what's wrong with that?
So the ratio for the height, the radius of the bigger
To what?
to
Where to go?
It should tend to 1, but
Okay.
it should
All right.
not like a curve.
All right. What about the opponent? Opponent, you see the point? Okay. All right. Any more questions? Maybe everyone is tired. All right. So let's come to the scoring time. So ready? Well, take your time. Take your time. All right. Score for reporter. Start from me. 4, 5, 5, 5, and 5. Let's go for opponent. Start from me. 7, 7, 7, 6, and 6. Comes to reviewer. Start from me. 7, 6, 6, 7, and 6. Pretty much. Jura want to say
Once
something?
again, for reviewer, I didn't copy.
Reviewer was,
Once
yeah.
again, review.
I'll read it again. 7, start from me, 7, 6, 6, 7, and 6.
Thank you.
All right. So, I'm wondering if you would like to say something or any comments to that? Just for education. Yeah. All right. I'll conclude this session. Thank you all. Thank you.
Thank you.